Okay, so what we've got here is a little semester exam review video. We're going to review some topics that might be potentially troublesome for you on the semester exam, maybe just some things we haven't talked about in a while. And so let's go ahead and simplify this expression. Remember, this is an expression because there's no equal sign, okay? So we're not solving it like we do an equation. We're not going to know what k is at the end of this, but we should end up with an expression. So first thing I want to know is I want you to just kind of go on your own and work this out on paper. I want you to simplify the expression first before I walk through it. Okay, and so as I walk through it, I'm going to start by distributing this negative like it's a -1, and I'm also going to distribute this -2 right here, okay? So first off, that minus in front of the parentheses, you distribute it just like it's a -1. It's going to change the sign of everything inside the parentheses. So that becomes -k plus 4. Then I still have my 3k, and here's where you got to be careful. When we're distributing here, you want to distribute this 2, but also the sign in front of it. Since this is a negative, it is going to change the signs of these two values inside the parentheses. So -2 times 17 is -34, and -2 times -k, a negative times a negative is a positive. Now that we have distributed, we're ready to combine like terms, and I see that I have two types of terms. I have terms with k, and then I have a couple of constants. So if I combine those constant terms, that's just 4 plus -34. That's going to be -30. And then I can combine these terms with k. Let's see, I've got positive 2k plus 3k, and then minus 1k. So 3k plus 2k, these two together would be 5k, and if you take away 1k, that should be 4k. So that is our simplified expression. That is as simple as it gets. I think that a common mistake people would make is that they would try to maybe subtract 3k here and subtract 3k here as if these were on opposite sides of an equation. But remember, since there's no equal sign between those, we just combine the like terms. We just add them together like we did here. Okay, in this next example, we are going, or really our next two examples, we're going to solve equations. So what I'd like for you to do here is I'd first like you to stop and solve for r. And I'm going to walk through this one. Once again, we've got this negative sign out in front of the parentheses. It's like we're distributing a -1 into our parentheses. Notice the 12 does not get distributed because it's not touching the parentheses, just the minus. So I'll still have my 12, and then we have -7 plus 4r. We get that because the negative times the negative is a positive, and then that's still all equal to 10r. Now we've got an equation with variables on both sides, but really, I mean, there's a few different ways you could go next. But first off, I see that I've got some like terms right here on the same side of the equal sign, and I can just combine these. 12 minus 7 would leave me with 5, and then I've still got my 4r equals 10r. We have an equation with variables on both sides. Remember, our strategy typically on these is to try to get all of our variables to one side of the equation and try to get all of our constants to the other side of the equation. Well, this 5 right here is our only constant, so I can just leave it on the left side of the equation, and that means I want to try to get my terms with r to the other side of the equation. And so our way of doing that, in order to get rid of this entire term, is subtract 4r from each side. And so then I've still got my 5. That cancels, and that's equal to 10r minus 4r, which would be 6r. My last step is to divide by 6 on each side, and I have that r equals 5, 6. Okay? Yeah, let's go ahead and jump to our next example. We got another example of solving equations. This time we are going to solve equations with fractions. Okay? I'm going to challenge you to leave this as a fraction and don't convert it to a decimal. I think what we do is we convert these to decimals, and really this particular fraction isn't too bad, but sometimes we have fractions that are repeating decimals, and when we round them we lose accuracy. Okay? So once again, I want you to go ahead and solve this on your own and put in your answer, and then we'll come back and I'll work through it. I'm going to start by, since we're trying to isolate the m right here, that means I want to get rid of the other stuff that's over here with the m. I want to isolate the m and get it by itself, so I'm going to get rid of this 3 first by subtracting 3 from each side of my equation. That leaves me with -1 equals 2/5 m. Now, here's where we struggle a little bit. There's a few different ways to go about isolating this m. Some of you might like to multiply by 5 and then divide by 2. Some of you like to multiply by the reciprocal. If you do those things and that works for you, great. I'm going to show one particular strategy. We see that we have m times 2/5. This is like a coefficient. It's being multiplied by the m. So our inverse operation is going to be to divide by whatever that coefficient is. So I'm dividing both sides of my equation by 2/5. And so the question is, what is this over here? And the way that we divide fractions, and I'll come over here and we'll do some aside work to work this out. I have -1 divided by 2/5. Well, if we remember how to divide fractions, what we do is we flip the second and multiply. So I can take this second number, I can flip it, and then I change my division to a multiplication. Now, we're multiplying an integer times a fraction, but any integer is really just that value over 1. So we can do that and multiply straight across. -1 times 5 is -5. 1 times 2 is 2. That means this is the same thing as all this stuff right here. That means that's our final answer. Our final answer is m equals -5/2, which is equivalent to -2.5. All right, let's jump to our next one. Transformation. So we want to describe the transformations that takes place as we change f of x into g of x. So that means we got to describe how this graph would change to get to this graph. Okay? So I'm going to go ahead and let you work this one out and answer it, and then I'll come back and work it out for you. All right, so what I'm going to do on a problem like this is not so they actually give us the equations. So I can actually just graph this and graph this and then just describe the change, okay? What we see here with our f of x is that it's f of x equals 2x or 2x plus 0. That means that's our y-intercept, and the value next to x is our slope. So if I come over here to graph, that means I'm starting at the origin. That's the y-intercept, and then I can rise to and run 1, okay? Rise to and run 1, and that's going to be our line. So I'm going to get rid of these other lines, but it's basically going to go like so, and I will just draw my line through it. I'll draw it as straight as possible. But this line that I've drawn right here, this is our f of x, okay? And then let's draw g of x, because once we graph this one, we can get a look at the two and kind of compare them. But g of x is 1/4 x minus 5. Well, the minus 5 right here, that means that our function is going to be shifted down 5 units. 1, 2, 3, 4, 3, 4, 5. That means that's the y-intercept of our new function, okay? That's the y-intercept, so it's been shifted down. And then it looks like our slope has changed as well. But our slope is 1/4, so that means I can, starting at this point, I can rise 1 and run 4. And I'm kind of going off my graph a little bit, but I can rise 1 and run 4 the other direction. And we end up with a graph that looks like this. And so really, when I see this, I see two changes that took place. I see, for one, our graph shifted down 5 units. Okay? And we could have known that before we graphed just by comparing the y-intercepts. This y-intercept controls the vertical shift. As this number increases, our function shifts up. As this number decreases, our function shifts down. Since we went from 0 to -5, our function shifted down 5 units. And then the other change that happened, change number 2, has to do with our slope. So we see that our slope changed from 2 to 1/4. It got from a number that was further to 0 to a number that's closer to 0. So our slope, or the line, was vertically compressed, is what we call that. We call that a vertical compression. And I'll put in parentheses, it was made flatter. Because if we remember, the closer that slope gets to 0, the flatter our line is going to get. Because remember, a 0 slope is a perfectly horizontal line. Since 1/4 is pretty close to 0, that means this slope is going to look a little more like 0. It's going to be a flatter line. It's going to be compressed. It's like it's being squeezed from the top and from the bottom to make this flatter line. So those are the two changes that are made as we change f of x into g of x. Here's our last example, and this is just a question I pulled off of one of our tests from earlier in the year. But we're looking for when the coyote population decreased at the greatest rate, okay? So once again, like all these, I'm going to pause, let you work it out, and then I'm going to come back and work this one out for us. Okay, so I'm kind of looking at my table. I want to look at the change because we're kind of looking at where it decreased at the greatest rate. And I see, okay, right there, it decreased by 4, and then it looks like it decreased by 10, and then it decreased by 2, and then from 68 to 59, I believe that's a decrease by 9. And so when you look at this, you might say, oh, okay, so there in this little interval, it decreased by 10, and so that means that from the year 2000 to the year 2003, that's where it decreased at the greatest rate. And that's what a lot of people are going to say, but that's actually incorrect. What we have to remember, and this is important, is that our rate of change or our slope is defined as the change in y over the change in x. In this case, that would be the change in, we'll say, the change in the number of coyotes over the change in years. So if you're only looking at these values, you're completely ignoring the change in years. This is our change in x up here. So we have to create ratios to make rates of change here. We cannot just look at the change in y, because I think we'll see something interesting here. Here, to go from 1998 to 2000, that's an increase of 2. And then an increase in 3, an increase in 1, and then an increase in 2, okay? And so if we actually turn these into ratios with our change in y over our change in x, let's see what we get. Here I get negative 4 over 2 for that first one. Here I get negative 10 over 2. Excuse me, negative 10 over 3. I got that from negative 10 over 3. Then we got negative 2 over 1. And then we got negative 9 over 2. So let's see. Let me simplify these to get our answers. This becomes negative 2. That's really, I can go decimal with it, I guess. And then that's negative 2, and that's negative 4.5. Okay, and now what we see is it looks like here from 2004 to 2006, this is when it's decreasing at the greatest rate. Okay? And so if we only look at the change in y, we might assume that from 2000 to 2003 it was decreasing the fastest, but look, it decreased by 10, but that's over the course of 3 years. Decreasing by 9 over 2 years is actually decreasing at a greater rate. So we have to look at change in y over change in x. This is our answer from 2004 to 2006.